Swayam Prabha. Digital India. Educated India.
Hello everyone. So today we'll start our next topic, that is the normal aspects of ECG and the technical aspects. Along with this concepts we will cover, that is ECG calibration, how calibration is done in the ECG machine, what are the different types of ECG leads, and what is the importance of the Enthoven's triangle, what are the configuration of different waves. Now, in the last lecture we had already studied the different types of waves in the ECG. We have P wave, we have QRS complex, Q wave, R wave and S wave. Then we have seen the T wave. So, the 5 types of waves we have seen. We will do a brief recap of whatever we had done in our last lecture. Now, this is initially the atrial depolarization. Atrial depolarization means SA node, travelling of the impulse from SA node to the AV node. So, atrial depolarization will give you the P wave. So, this is your P wave. So, atrial depolarization, that means after the atrial depolarization there will be contraction of the atrial musculature. So, the electrical events which is occurring in the atrial, that is impulse transduction from SA node to AV node, is giving rise to your P wave. Now, after the complete depolarization of the atria, we get an isoelectric line that usually constitutes the AV nodal delay, because the conduction in the AV node is very slow and the ECG machine cannot detect that voltage signals. So, we get an isoelectric line. So, after that we get the ventricular depolarization, which occurs in 3 phases, that is septal depolarization, then the whole ventricular myocardial depolarization, and the last portion of the heart to get depolarized, that is the basal portion. So, we get the septal depolarization from left to right direction, then we get the major vector directed towards the left lower portion, that is the ventricular musculature depolarization, myocardial depolarization, which occurs from inner myocardium, that is endocardium, to outer myocardium, that is epicardium. Then the last portion of the heart to get depolarized, that is the basal portion of the heart which gets depolarized, and so hence we get QRS complex. Now, while getting this QRS complex, we are actually saying that the ventricular muscles are getting depolarized. When the ventricular muscles are completely depolarized, we get this ST segment. So, this ST segment is also an isoelectric line, followed by the T wave. T wave is nothing but ventricular repolarization, where the repolarization occurs from the opposite direction, that means from the outer portion of the myocardium, that is the epicardium, to the inner myocardium, that is endocardium. The reasons are all been described in the last lecture. So, what is very important to know is, during the ventricular excitation or ventricular depolarization, another event is coinciding with the ventricular depolarization, which means atrial relaxation. Atrial relaxation is a mechanical event. So, we get an electrical event, that is atrial repolarization. So, where does this atrial repolarization will go? So, this atrial repolarization actually overlaps the ventricular depolarization, and since the atrial musculature is very thin, so we do not get to see the repolarization waves. What we see is the depolarization of the ventricular waves, that is QRS complex, and that usually mask the atrial repolarization waves. So, if we want to stress the atrial repolarization waves, so that will be in the negative direction. So, this is all about your last class which we had already described. So, now we will move on to the calibration of ECG. So, electrocardiogram is the recording and electrocardiograph is the machine, and the process is known as electrocardiography. So, ECG paper is a strip of paper which is thermosensitive paper, and it contains vertical as well as horizontal lines. Now, this horizontal lines denotes the time, which is usually represented in milliseconds or seconds. The vertical usually denotes the amplitude or the voltage, which usually represented by millivolt. So, the horizontal axis gives you the time, that is represented by milliseconds or seconds, and the vertical axis gives the voltage, the deflections or the amplitude. Now, in the ECG paper, what conventional ECG paper, what we see, the strip of the paper is usually moved at a speed of 25 millimeter per second. We set the speed, there is other speed also, we nowadays we see in the machines we have 50 millimeter per second, but we usually keep the speed at 25 millimeter per second, which means 25 millimeter of the paper is moving in 1 second. Now, we get to see number of boxes, we get to see the large, this is the large boxes or large square. It consists of 5 into 5, that means 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5, 5, 25 other small squares also. So, one large square consists of 25 small squares. Now, what the calibration need to be done, how the calibration is done in the ECG? It is to be done so that 1 millivolt gives a deflection of 10 millimeter. Now, usually this small square which is present in the big square. So, this small square horizontally it is 1 millimeter and vertically also it is 1 millimeter. That means, the dimensions is 1 by 1, 1 into 1 millimeter square millimeter, that is the area of the square. So, the vertical deflection how it will give? So, 10 millimeter, the calibration is done in such a way that a voltage deflection of 1 millivolt will cross the deflection of the needle of 10 millimeter. That means, 10 millimeter is giving a deflection of 1 millivolt. So, 1 millimeter will give a deflection of 1 by 10, that is 0.1 millivolt. So, that means, vertically if this is one small square, this is the vertical and this is the horizontal axis. So, vertically 1 millimeter corresponds to 1 millivolt, and as I told you, the horizontal axis gives you the, that is the x axis gives you the time in milliseconds. So, how much will 1 millimeter of the square will constitute? So, 25 millimeter is equal to 1 second. So, 1 millimeter will 1 by 25, that means 0.04 seconds. So, 25 millimeter is equal to 1 second and 1 millimeter will give 0.04 seconds, which means the horizontal axis or 1 millimeter of this square corresponds to 0.04 second. Now, this millivolt deflections, this values of time duration 0.04, these are all important for calculating various segments, various intervals, various waves, the P waves, the QRS complexes, the T waves, what is the duration, what is the amplitude, the interval and the segments duration. So, these are very important. So, this we will learn further in the next lecture when we will do interpretation of the ECG. So, for the time being you have to remember the speed of the paper is 25 millimeter per second. The calibration is done in such a way that the horizontal axis of 1 millimeter gives the time duration of 0.04 seconds and the vertical deflection of 1 millimeter gives a deflection of 0.1 millivolt. So, with this calibration, now we will move on to various ECG leads. As we have seen in the previous lecture that our body is an excellent volume conductor, it is an excellent conductor of electricity. So, whatever electrical currents are generating in our body, So, whichever currents, since we are recording, the ECG is a recording which is done extracellularly. So, on the surface of our body, if we are placing the electrodes, we could easily record those currents, electrical activity which are going on in our body. So, the current source, say suppose the heart is present in the center, how we place various electrodes, what are the reference points. So, generally we do a 12 lead ECG. In the 12 lead ECG, we have 6 limb leads and 6 precordial or chest leads. So, these precordial leads are nothing but the chest leads. Now, the limb leads, they usually measure the fluctuations or various electrical activity of the heart based on the frontal plane or coronal plane, while from the front they are measuring, that is the coronal plane or the frontal plane. But the chest leads, they usually measure the electrical activity from the horizontal plane, So, these leads are nothing but they are the pair of electrodes which are acting like a camera. So, we have 12 cameras situated superiorly, anteriorly, laterally, inferiorly. So, they are trying to capture various electrical activity of the heart from various directions. So, we have 6 limb leads which capture the electrical activity from the frontal plane, and we have 6 chest leads or precordial leads which capture the electrical activity based on the horizontal plane. Now, out of the 6 limb leads, we have standard bipolar limb leads 3, which is 1, 2 and 3, lead 1, lead 2 and lead 3, these are the 3 standard bipolar limb leads. Then we have unipolar limb leads, those are also 3, that is A stands for augmented. So, we will come to that later. So, we have AVR, AVL, AVF, again 3 unipolar limb leads, and we have V1 to V6, 6 chest leads which are located at different portions of the heart. Now, who are the inventors of these leads? Standard bipolar leads been discovered by William Enthoven. The unipolar leads been discovered by Goldberger, and Frank Wilson had discovered the chest leads. Now, William Enthoven is a very significant name over here because this person has got Nobel Prize for discovery of ECG in 1924. So, William Enthoven has discovered the standard limb leads, Goldberger the augmented unipolar limb leads, and the chest leads been discovered by Frank Wilson, V1 to V2. Now, coming to the standard limb leads, as I told you, the standard limb leads are nothing but they are the bipolar leads. So, what do you understand by the bipolar leads? Bipolar leads means if I have a voltmeter, ECG is nothing but that acts on the principle of voltmeter. They record the potential difference across 2 points because of the cardiac dipole which is created. So, if there is a voltmeter, so there will be one connection, that is a negative terminal, the other electrode will be having the positive terminal. So, if these two terminals or if these 2 electrodes, if both are active, it is known as bipolar leads, which means these 2 electrodes are recording simultaneously some or the other voltage, and the lead which is constituting these 2 electrodes, suppose this is the lead which will constitute these 2 electrodes, will measure the potential difference across these 2 electrodes, which means both of the leads, both of the electrodes are active in this bipolar leads. They are recording some or the other voltage, and the leads will calculate the potential difference between these 2 electrodes. So, in this way we have 3 leads, that is lead 1, lead 2 and lead 3. How these 3 leads are connected, we will see. So, suppose we keep the electrodes, we place the leads, we place this at the right arm, this is right arm, this is left arm, this is left leg and this is right leg. While conducting ECG, we usually place the one electrode in the right leg also. This right leg electrode is usually placed for grounding purpose. So, other 3 references. Now, whether you place the leads over the acromion process or you place the electrodes over the pubic symphysis, it does not matter. Whatever electric current is generated across your current source in the body. So, this electric current whichever is generated, whatever electric current is generated at the level of shoulder region or acromion process, the same current you will be getting in the mid of your arm, the same thing you will be getting at the level of your wrist. Similarly, whatever current is generated at the level of your left shoulder, the same current you will get at the level of your left wrist. Whatever current is generated at the level of your pubic symphysis, the same you will get at the level of your left knee or left foot. Now, it is very convenient to put the electrodes or the leads at the wrist region of the exposed part, that is right arm, left arm and the left leg, as compared to the placing these leads over the shoulder regions and the pubic symphysis. So, we put, since it is a volume conductor, our body is a volume conductor, we put the leads across the right arm, left arm and left leg. We put the electrodes. Now, this right arm, the negative terminal, if we connect a voltmeter over here, how this lead is created? The negative terminal of the voltmeter is connected to the right arm, the positive terminal of the voltmeter is connected to the left arm. This constitutes your lead 1. That means, lead 1 will calculate the potential difference between the left arm voltage and the right arm voltage. Similarly, if the negative terminal of the voltmeter is connected to the right arm and the positive terminal of the voltmeter is connected to the left leg or the left foot, it usually constitutes the lead 2, which means lead 2 will calculate the potential difference between the left leg and the right arm. Similarly, if the negative terminal of the voltmeter is connected to the left arm and the positive terminal is connected to the left leg, this constitutes your lead 3, which means it will calculate the potential difference between your left leg and the left arm. So, in this way we could see these 3 leads are connected and we get an inverted equilateral triangle. So, this inverted equilateral triangle is bearing a current source, that is heart at the center of it, and these are the 3 leads connected. So, this triangle is nothing but known as Enthoven's triangle, named after the scientist William Enthoven. So, with this we will see what do you understand by Enthoven's law. Enthoven's law states that, we will take an example, suppose the electrode measurements we have got in the right arm, this is right arm, this is left arm, this is left foot, obviously right foot has been grounded. So, the voltage measured at the right arm is minus 0.2, the voltage measured at the left arm is plus 0.3 and the voltage measured at the left leg is plus 1 millivolt. So, what will be the potential difference across all these 3 electrodes? That will constitute your nothing but 3 leads. So, lead 1 obviously it is between the right arm and the left arm. So, it will give the potential difference of 0.3 minus of minus 0.2 millivolt, that means 0.5 millivolt. So, it is giving a potential difference of 0.5 millivolt. Similarly, lead 2 will give a potential difference of 1.2 millivolt. How? Because 1 millivolt minus of minus 0.2, that will give 1.2 millivolt. Similarly, the lead 3 will give, this is lead 1, this is lead 2 and this is lead 3, will give a potential difference of 0.7 millivolt. How? By 1 millivolt minus 0.3, that is 0.7 millivolt. So, you can see over here that lead 2 is equal to lead 1 plus lead 3. Lead 2 is having 1.2 millivolt, lead 1 is having 0.5 and lead 3 is having 0.7 millivolt. So, this is nothing but your Enthoven's law. That means, the summation of the vectorial summations of the voltage or the potential difference of lead 1 and lead 3 is equal to the lead 2 voltage. So, this is your Enthoven's law. Now, coming to the augmented limb leads. As I told you, augmented limb leads are known as unipolar leads. Now, what does unipolar leads mean? Bipolar leads mean the two electrodes are active across the voltmeter. Now, again, in case of voltmeter, if one is connected to the negative, the other is connected to the positive. Suppose this negative electrode is inactive and this positive electrode is active, or it is also known as exploring electrode, which will record the voltage at a particular point. Now, negative electrode is inactive means this is made inactive by keeping it fixed. A very specific term can be used, that is a fixed, that means the voltage is fixed and this voltage is usually made close to, not exactly equal to 0, but it is made close to 0 millivolt by combining it with high resistance. So, when we combine the electrode terminals with very high resistance of, say, suppose 5000 ohms, so we get the voltage across this that is equivalent to 0. Practically or mathematically we do not get 0, but we get the values close to 0. So, it is better to use fixed term in this case. So, the other electrode is active and the positive electrode is active, or the exploring electrode, whereas the negative electrode is inactive. So, augmented limb leads are usually again 3. We have AVR. A stands for augmentation. AVR means the augmentation of the right arm voltage. AVL is the augmentation of the left arm voltage. AVF is the augmentation of the left foot or the left leg voltage, which we have already seen in the limb leads. And generally this augmentation is 50%. How much the voltage is increased? That means the amplitude of this voltage is increased by 50%. Suppose in the limb lead, if we get the voltage of 10 millivolt at right arm, so we will get, by augmentation, we will get 15 millivolt at right arm. So, this 15 millivolt is the augmentation done. This augmentation is done for prominent recording. So, how this augmentation is done, we will see with this AVL. So, AVL means I have to keep my active electrode or the positive electrode at the left arm, and the negative electrode or the inactive electrode, how I will combine? I will combine this right arm and this left leg with high resistance. This resistance is around 5000 ohms. So, mathematically the voltage, if we calculate over here, it will be V, that is voltage of right arm plus voltage of left leg divided by 2. So, this voltage will be so minimum that it will become close to 0 millivolt, and that is why in this way this is considered as to be the negative electrode. So, the positive electrode is left arm where it is connected to the voltmeter, and this will this is also called as exploring electrode. In this way AVR is also augmented and AVF is also augmented. In AVR, right arm is connected to the your active electrode, whereas high resistance is connected with the left arm and the left foot, and in case of AVF, the left leg is connected to the active electrode, whereas the right arm and the left arm is connected with the help of high resistance to the negative or the inactive electrodes, that is made inactive. So, in this way unipolar leads or augmentation of the leads is done by 50%. So, this unipolar leads as well as the standard limb leads, the 6 leads, they constitutes the hexaxial reference system, which means they are located at a certain angle. We have already seen lead 1 to be at 0 degree, lead 2 is at 60 degree, lead 3 is at 120 degree. These are the standard limb leads angle orientation, lead 1 0 degree, lead 2 60 degree, lead 3 120 degree, which means in the downward portion the deflection goes, it is a positive, whereas the upward portion is negative. That is why we see AVL to be minus 30 degree, AVR is minus 150 degree, and AVF is 90 degree. So, these are the angles we have to remember for the hexaxial reference system of the limb leads, whether it is standard limb leads as well as the unipolar augmented limb leads. Now, what are the configuration of various waves in this hexaxial reference system? So, first we will see about the P wave. Now, P wave is only the one wave, it is the atrial depolarization. So, we can see various instant vectors are travelling from SA node to AV node. We get various vector which travels from SA node to AV node. So, in this way, but our ECG records the mean of all these vector, which is known as mean instantaneous vector. So, the direction of the mean instantaneous vector is this one from SA node to AV node. Now, if we put this on the reference of the hexaxial axial system, what we see, whichever leads are present at this direction, they will give the positive deflection. Whichever lead is present at this direction, they will give the negative deflections. That means, when the wave of depolarization, it has already been told, is moving towards your recording electrode, it will give a positive deflection, and when the wave of depolarization is moving away from your recording electrode, it will give a negative deflections. Now, the deflection depends on the angle of the lead situation of your leads. For example, in this case SA node to AV node means atrial depolarization, we will get P wave, which means we will in the lead 2, as we can see the green direction, it is almost parallel. So, it will give a deflection, say suppose of 10 millivolt, but in case of lead 1, it will give a deflection, it will definitely give a positive deflection, but this deflection may not be of the 10 millivolt or which we had seen in the lead 2, it will give a deflection of suppose plus 2 millivolt. Similarly, in case of lead 3 or AVF, we can see the deflection of P wave may be of plus 5 millivolt. So, the amplitude of the deflection varies along with the situations or the positions of the leads based on their angles. So, we can see the P wave how we have got. So, AVR is the lead which is giving the negative deflections of the P wave, because it is situated just opposite to this direction of the wave of depolarization. Now, coming to the ventricular depolarization, we get 3 waves. We will see how this ventricular depolarization fits in the hexaxial system. Now, this is the lead 1, lead 2 and lead 3 standard limb leads. This is lead 1 0 degree, this is 60 degree and this is 120 degree lead 3. These are the leads of the augmented limb leads, AVL minus 30, AVF plus 90 and minus 150 degree, that is AVR. Now, ventricular depolarization occurs in 3 parts. The first is the septal depolarization, the second is the maximum myocardial ventricular depolarization, and then we have the basal depolarization of the heart. So, the directions are different. This is the left to right direction of the septal depolarization, which means the septal depolarization is moving from left side to right side. So, this is left and this is right. So, whichever leads are present on the right side, they will give the positive deflection, and whichever leads are present on the left side, they will give the negative deflection. So, based on the rules, we get these are the Q wave which we see in the QRS complex. The AVR is giving a positive deflection, lead 3 is giving a positive deflection, AV is giving a positive deflection, while AVL 1 and 2, these are giving the negative deflection. So, negative deflection means this is the Q wave. The positive deflection means this is not the Q wave, because the first positive deflection after P wave is R wave. So, these are the R waves, not the Q waves. The next ventricular depolarization is the maximum ventricular vector which we get towards the lower and lateral side, and according to this vector, what is the R wave configuration we get? We see whichever leads are present as per according to this towards this vector or wave of depolarization, they are giving positive waves. That means AVL, AV1, 2, AVF and AV3. Again the deflection, as I told you, the amplitude of this deflections depends on the angle of the leads, and AVR is of course, since it is in opposite direction to the wave of depolarization, it is giving the negative deflection. Now the last depolarization is the basal portion depolarization. So obviously the leads which are present this inferiorly, this will give the negative waves, that means the negative, this is the S wave, whereas the wave the leads which is present towards the wave of depolarization, the basal portion of the heart depolarization, that will give the positive deflection, which is usually seen in case of AVR. So what we can see in this is whole about the configuration of the QRS complexes in the hexaxial system. So we can see there are no Q waves or the first negative wave in case of AVR and lead 3 and also AVF. So now we will see what are the chest leads. Chest leads are also known as precordial leads, and this is also unipolar leads. These are also known as unipolar chest leads. As I told you, unipolar means the one of the electrode which is connected, this will be active, the other electrode which is connected to the negative terminal, that will be inactive. So we have V1 to V6. The 6 chest leads are placed at the different portions of the heart. So for example, if I want to measure, I want to measure the voltage or record the potential difference across the V1 chest lead. So this, how I will measure the positive terminal of the voltmeter, I will connect to the V1, and the negative terminal of this voltmeter will be connected to a terminal known as Wilson's terminal. As you remember, the chest leads been discovered by Frank Wilson. So this terminal is named after Frank Wilson. So Wilson's terminal. Wilson's terminal is nothing but it is a terminal where the right arm, left arm and the left leg, these are joined at these 3 electrodes are joined at high resistance of 5 ohm each, and this is connected to the Wilson's terminal or the negative terminal of the voltmeter. So actually mathematically this voltage of right arm, voltage of left arm, voltage of left leg divided by 3 should give the voltage of this negative terminal, Wilson's terminal, which is considered to be equivalent or close to 0. So in this way we get the chest leads measurement or recording. If we want to measure V1, we will connect the positive terminal to V1. If we want to measure the potential difference of the voltage activity or electrical activity of V2, we will connect it to V2. In this way the positive electrode is connected to V3, V4, V5, V6. Now we will see how these leads are placed. Now on the chest leads, generally we have 3 reference point. This is known as mid clavicular line. It runs between the 2/3 and the 1/3 of your clavicle bone. It runs vertically. Then we have the anterior axillary line. It starts from your anterior portion of the axilla, anterior axillary line. Then we have the middle axillary line. We have the mid axillary line. Now these 3 references are very important in placing the electrode. We will place the electrode V1 at the level of right fourth intercostal space, just lateral to the sternum. So this is the sternum. So we are placing, this is the right and this is the left portion of the heart. We are placing V1 at the level of 4th intercostal space at the right side of the sternum. V2 is placed at the level of 4th intercostal space on the left side of the sternum. V3 is placed between V2 and V4. V4 is placed at the level of 5th intercostal space in the mid clavicular line. V5 is placed at the level of left 5th intercostal space in the anterior axillary line. V6 is placed again at the level of left 5th intercostal space along the mid axillary line. Now the question comes, how I will determine the intercostal space, how I will know which one is left third intercostal space, fourth intercostal space or fifth intercostal space. Now, for that we have to palpate the jugular notch. Then this is the jugular notch. From jugular notch we will palpate the sternal angle of Lewis or angle of Lewis. The sternal angle of Lewis usually corresponds to the second intercostal space, and if we just see the second intercostal space, if we just correlate with the sternal angle, then we can usually easily count which one is second, third, fourth, fifth, and in this way we can place the leads accordingly. So, in this way the chest leads or the precordial leads are placed. We have to remember the location of these leads. Now, how this chest leads are depicting the various waves. Now, this V1 to V6, they are placed in I told you the horizontal plane. Chest leads is measuring the it is capturing the electrical activity from the horizontal plane. So, V1 and V2 measure the septal activity, V3 and V4 anterior activity of the heart, and V5 and V6 lateral activity of the heart. So, we can see the first septal depolarization which occurs from left to right, that means the V1 and V2 will give the positive deflection, and that is what it is giving, the positive deflections. We get the R wave, we do not get to see the Q wave over here, and this R wave generally, because of the ventricular maximum ventricular depolarization which occurs in this direction, we see an R progression, R wave progression. We can see this R wave amplitude is increasing at the maximum to the V5 level. So, this is known as R wave progression. It is very important phenomenon to look for whenever we are interpreting ECG. So, R wave progression occurs from V1 to V6. There are no Q waves present in V1 and V2. V3 is generally giving a biphasic waves, and V4, V5, V6 generally gives the maximum or the tall R waves. Now, this hexaxial system along with the chest leads, they denote the various activity of the heart from different level. So, the septal leads, the septal portion is denoted by V1 and V2. The inferior portion of the heart is denoted by lead 2, lead 3 and AVF. This is the inferior portion. The lateral portions and the anterolateral portion is denoted by anterior portion, specifically V3 and V4. The lateral portion is V5, V6, lead 1, AVL and AVR. Now, why this so many leads and different portions are important? Because whenever we get a disease pathological condition, myocardial infarction, we need to know which portion of the heart has been damaged. So, that is why so many cameras and so many leads are required to view the electrical activity of heart. So, as per the QRS nomenclature, we must remember the first negative deflection which occurs after P wave, that is Q wave. It can be small q, it can be large q, it depends on the amplitude of the deflection. If the amplitude of the wave is less than 3 small squares, generally we refer to as the smaller alphabetical letter. Then the first positive deflection is R wave, it can be small r, it can be large r, depends on the amplitude. The negative deflection after R wave is S wave. The positive deflection after R wave is R prime. So, suppose this is your normal QRS complex. This is the first negative deflection which is Q. This is the R positive deflection in the QRS complex, the first positive deflection in the QRS complex, and this is the negative deflection after the R wave. So, this is S wave. So, suppose we get an wave like this. So, this is the first positive this is the positive deflection. So, this is R wave after P wave, but this is the negative deflection which we got after R wave. So, this will not be Q wave, this will be S wave. Similarly, if we get the second positive deflection after R wave, so this will be R prime. So, these are the QRS nomenclature you have to remember. We have till now we have seen unipolar chest leads. We also have bipolar chest leads, which is known as Lewis chest leads. These Lewis chest leads are nothing, these are the bipolar chest leads, which is usually placed to record the atrial flutter. So, this is the summary of your ECG. We can see this is the 12 lead ECG, lead 1, lead 2 and lead 3, these are usually biphasic. The augmented limb leads AVR, AVL, AVF. AVR is giving almost all the waves negative deflections. This is a very important point to look whether you have placed your leads correctly or not. Then AVL and AVF biphasic. V1 and V2 we can see deep S waves, the negative deflections, but we do not see Q waves. V3 and V4 biphasic, and V5, V6 we see tall R waves and small Q waves. Before concluding, an extra edge to this topic is His bundle electrogram. Now, what is this His bundle electrogram? Suppose this is a SA node and this is the AV node. Now, whenever we want to, if we want to see any activity in the AV node or the bundle of His, after bundle of His there is a depolarization of the ventricles which is done by the right bundle branch and the left bundle branch conducting system. But we do not get the recording of AV node and the His bundle in the normal conventional ECG. At that time we have to do an invasive procedure, that is cardiac catheterization, where we insert the catheter with an electrode on the tip through a peripheral vein close to the tricuspid valve to measure the activity of AV node. So, whenever impulse is travelling to the AV node, whenever it comes to the AV node tip, we get the AV node activation. After that, when it comes from tip of the AV node to the tip of the bundle of His, that means when it activates the or depolarizes the bundle of His, we get H wave in the His bundle electrogram. After that, when this whole bundle of His is depolarized and it starts the ventricular depolarization, we get this V wave. So, if we just correlate this His bundle electrogram with the ECG, we can see this A wave corresponds to the mid of the P wave. This H wave comes in between the A and the Q segment or the R segment, in between the P and the R segment, P and the R wave, that is middle of somewhere in middle of the PR interval, and this ventricular wave V wave corresponds to the Q wave obviously, which gives the onset of the ventricular depolarization. So, which means the the conduction from SA node to AV node is your SA node to AV node is around your 30 milliseconds. Now, this conduction has already been told in the conducting system chapter. Then the time taken from AV through the AV nodal conduction, this AV nodal conduction is nothing but this AH, this is your AV nodal delay. So, this is around 100 milliseconds, and the HV conduction is your bundle of His conduction, this is around 40 milliseconds. So, if I say the P wave onset, you can see this is the P wave onset. This P wave obviously it will occur before the A wave. So, this PA interval is 30 milliseconds. So, this PA interval plus AH interval plus HV interval will give nothing but your PR interval. So, if we want to pinpoint where is your block in the heart, whether it is at the level of AV node or bundle of His, then we have to do this study, invasive procedure of cardiac catheterization, that is His bundle electrocardiogram. Otherwise, in only ECG, the block will be detected as prolonged PR interval. It will not be able to say where exactly the block is located, whether it is at the level of AV node or the bundle of His. So, with this we conclude today's topic. So, these are the references from where I had taken the lecture. Thank you.